Well, hey, it is 2 hours UTC, and it's time again for Astronomy Daily Live. So welcome, everybody. Welcome. Come on in. Join the ever-growing circle of friends that gets together pretty much every single day, and gets together on this virtual porch of ours. We're sitting in our lounge chairs, sort of outside. The sun is setting. The sky is clear. It's a fantastic temperature. We're out in comfortable clothes, and we're gathering together just to sit back and enjoy thinking and talking all things astronomical for at least the next hour-ish or so. We've got some nice space music in the background here. Hope that's okay. Let me know if it's too loud or too soft or anything. Here I think it's just about right. So let me know. I'm going to look in the chat. Tim, nice to see you in the chat. Another late night for you over there. Larry, hey, nice to see you. Anyone heard that Christmas song Jethro Tull, Ring Out Sausage Bells? No, I don't think I've ever heard that one before. So don't know what's going on. Hey there, Bobby. Nice to see you. Nice to see you. Did I not send the link? Is that no, I think I did. Yeah, I think I did. Okay. One never knows. One never knows. So yeah, hope everybody's doing well today out there in the world and the universe. Everything's good here? Yeah, everything's going really, really well. It's been a little bit cold, relatively speaking. So yeah, so grab your favorite consumable of choice. I usually reach for the grand molecule, the master molecule, the hydrogen hydroxide, HOH, and it's pretty awesome. So cheers. So yeah, hope everybody's doing well out there. I wanted to yes, Tim, put on the kettle. You gotta keep yourself awake. So, all right, well, cool. Larry, only in the virtual sense. Is that possible? So feel free to hang out. Hey there, Ray. Nice to see you again. Yeah, really, really nice to see everybody here. Hope everybody's doing well. We're just doing the kitty thing here for a little while. They definitely like these kinds of things. Although it's got to be a little bit frustrating. It gets wet really quick, so it's like yeah. So, but yeah. All right. Well, cool. So I'm going to be saying this all week long. This is Solstice week, right? In fact, if you look on the chat, right, I can type in a Nightbot command called Solstice, and it will tell us how many days, how many hours, how many minutes, how many seconds to the December 2018 solstice. And it looks like it's in 5 days, 28 hours, 18 minutes. So this year, the solstice, the December solstice, that takes place on the 21st of December at 22:23 UTC. So for some of you, like Tim, that is going to be late in the evening. So, you'll sort of experience experience that in sort of an indirect way, right? I am lucky enough to actually be 7 hours behind UTC. So 22 minus 7, right, is 15, right? So at 15, 23, whatever it is, I forget exactly. We're going to have to find out exactly. You know what? I can look on, I've got that in the Nightbot command. So let me just look really quick, and because otherwise I'd have to look it up somewhere else. Okay, so 1523, right? So 3:23 p.m. Mountain Standard Time is when the solstice takes place at my location. And what I like to do, and now you don't want to do this for very long, right? But what I like to do is at that moment, right, I'll glance up at the sun, just, just sort of a quick look, to say howdy, because the sun is as low a declination as it's going to be for the entire year. So I just like to take a glance at the sun and say, hey there, you're really, really low, and welcome it back up, right? Because from that point forward, it's going to be moving north. One can say also, and there's some funny things about the timing of all these things. So I may not be exactly right, but solstice is, I believe, the point where the sun has actually stopped moving in declination, right? It's moved as far south as it's going to be, and it's going to be coming back up north. So at that point, when it stops and then moves back up, right? At that point, that I believe is the solstice. And at that point, I like to glance at the sun, give it a wave, and say, glad you're coming back. So glad you're there, right? I'm pretty grateful that the sun is there. It seems to be pretty important. So it's pretty bright, so it's probably pretty important, I would think. So I like to sort of acknowledge the existence of the sun, and pay it a lot of respect. And Ray, halfway out of the dark. So, and of course, all this is reversed for friends in the southern portion of the planet. So yeah, longest, well, at least in the north, it's the longest night of the year and the shortest day of the year. And in the south, it's the longest day of the year and the shortest night of the year. So yeah, that's one of the problems with living on basically a sphere, right? I think technically, right, the Earth is what's called an oblate spheroid, and it's actually worse than that, right? Because it's bumpy. The interesting thing, and here's a little bit of trivia for you, is that if you shrunk the Earth down to the size of a cue ball, right? You play with pool, right? Or like a pool ball, it would actually be smoother, a lot smoother than that pool ball. So, if you've ever sort of held or looked at a pool ball and noticed how smooth that was, the surface of the Earth would actually be smoother than that. Okay, so things like Mount Everest and things like the that big deep basin down in what, the southwestern Pacific, Southeast Asia. You know, even those big grooves and those big huge bumps, Mount Everest, all the mountains, all that is actually smoother than a cue ball. So if you were to actually you know, do the opposite, right? Take a cue ball and expand it to the size of the Earth, all those hills, especially the hills, you know, the mountains and stuff, would collapse, right? Because there's just too much weight. So yeah, it's just an interesting thing. Now, having said all of that, Tim, this is just something that I've heard, right? So you know, this live stream is a lot of fun, casual, but it's skeptical, right? So I like to make sure that I'm not, you know, coming at this as some kind of an expert or a know-it-all, or, you know, I have no answers at all. But that's what I've heard, and it's actually pretty easy to figure out, right? I don't know. I'm going to make some really rough guesses here. We could look all this up, but I think the elevation of Mount Everest, or K2, is about, is it like, roughly speaking, about 30,000 feet above sea level, something like that. And the diameter of the Earth is something like 6,000 miles. I think that's about right. 6,000 miles in diameter. The height of K2, Mount Everest, is about 30,000 feet, or about 6 miles, right? In fact, about, yeah, 6 miles. Okay, really roughly speaking. So I have grabbed the calculator from the desk, and I say this all the time, right? Every good scientist has a calculator within arm's reach, right? And you saw that, right? I just went like this, grabbed it, right? Got to have a calculator. Not any of this computer stuff, not any of this phone stuff, right? Calculator. Yeah, okay. Well, Uncle Bill is giving us the actual numbers here. So Uncle Bill, hey there, Tom. Nice to see both of you in the chat, by the way. Since you're looking those kinds of things up, what's the diameter of the Earth in kilometers or meters as well? And basically, it's all I'm going to do is just divide those two numbers. So 8848 meters is 8.848 kilometers. DuckDuckGo calculates 8.848. And so, yeah, so the equator of the Earth is 40,000. That's the circumference, Uncle Bill. I believe that's the circumference. Yeah, I think the diameter is significantly less, but I can actually get the diameter that way, right? So don't sweat it. 40,075 divided by pi. That's it. Just got to incorporate some pi. What kind of pie? Any kind of pie. My favorite pie is peach pie. Peach pie, apple pie. Yeah, actually, my favorite pie is the infinite pie. So, okay, so that's 12,756 kilometers. And then I'm going to divide that into 8.848. And you see that it is point. So the height of the highest mountain on Earth is 0.065% of the diameter, right? So let's just see. A cue ball is I don't know, roughly. What do you think? About the size of your head? Yeah, not quite that big. A cue ball is maybe I want to say maybe 3 inches in diameter, something like that. Hey there, Tara Lee. Sorry about Nightbot. Nightbot is extremely sensitive, Nightbot needs to chill a little bit. I'm still kind of tuning that, but it's nice to see you in the chat anyway. So yeah, I think a cue ball is something like maybe, I don't know, 3 inches in diameter. Let's just say that, right? Nightbot needs a stiff drink to chill, man. Maybe he needs something else too. I don't know. He needs a chill pill for sure. All right, so I'm gonna store 0.065%. I'm gonna divide that by 100 again, so I get the right thing. So I'm gonna store that. So 3 inches is something like that's about 8 centimeters. 8 centimeters or so. Oh, Nightbot. Come on, Nightbot. Yeah, well, you know, Nightbot is a work in progress. We're kind of trying to see if it's useful. And there goes Uncle Bill. A cue ball is 52.5 millimeters. Okay, so 52.5 millimeters. Then I'm going to multiply it by that ratio between the height of K2 and the diameter of the Earth, which was 0.00065, right? Really, really small. So I'm going to recall that. So that's 0.036 millimeters. So let's see, that's a millimeter is 1,000th of a meter. So let's divide that by 1,000 and then multiply it by 1,000,000, because that will give us microns. Okay, yeah. So the equivalent height of a bump on a cue ball is 36 microns, right? So I think the thickness of a human hair is something like 100 microns, if I remember right. So yeah, so very, very small. I don't know how we got onto that. I have no idea. But yeah, so I'm glad everybody's here. You know, another thing that I wanted to do, and Tom, by the way, I think at some point when you come back onto the panel, let's talk some jazz. Let's talk some jazz. I'm very much into music, and I actually sort of discovered jazz maybe, I don't know, 5 or 6 years ago or so. I was in a jam band for several years, and that's when I started sort of beginning to understand jazz. Up until then, I was just like, what is this? You know, it's really, you know, kind of hard to understand where these musicians are coming from, right? But being in a jam band really, really helped sort of, you know, get used to jazz a little bit, and all the improvisation and everything. And now I absolutely love it, right? And if you haven't already, everyone, definitely check out jazzradio.com. I put it in the chat there. If you like jazz, they have, I don't know how many different genres there, and it's all free. You can, I think how it works is if you just come in and don't actually sign up or anything, I think you have a limited amount of time to play their stuff, right? But if you sign in, right, sign up, you can play all their stuff. You're going to have to deal with ads. Yeah, you know, the interesting thing, Tim, about metal is that there are a lot of elements of jazz in especially metal, especially, right? When those guys are just, you know, you know, it's there is definitely jazz in there, whether they know it or not. There is definitely jazz, and in fact, the I would venture to say that if you ask any metal player, and basically any good rock and roll musician, right? It's like, you know, what are the influences? Like you just said, right? Blues, classical, jazz. It's all there. In fact, Beethoven is serious heavy metal. Serious heavy metal. So is Mozart. Just insane. Bach is pretty metal too. It's just how it's played, right? And a little bit of extra fill, right? So yeah, you know, I can sort of definitely see this live stream from time to time going off on the music tangent, because that's another one of my big passions, big ones. Now, the passion for science and astronomy and everything is like way up here. The passion for music, maybe about here or so. So it's pretty high still, not as high as astronomy, not really even close, right? But I like it, and yeah, like I said, I just sort of got into jazz a few years ago, and it's absolutely fantastic. And so check out jazzradio.com. Like I said, you know, they got a whole bunch of different genres, and this time of year they actually have holiday jazz. So, you know, if you like to listen to Christmas music and all of that, set to jazz, that is the place to go. And I think that they have, you know, like paid subscriptions too. So, you know, if you don't want to deal with the ads that pop up, I don't know, maybe every half hour or hour or so, you know, you have to listen to a few ads. That's usually no big deal. But yeah, Ray, I am with you. I like practically all forms. I think, and don't hate me, okay? But I think one of the only forms of music that I really can't tolerate for very long, although I really appreciate the musicianship, but I really have a hard time for with bluegrass. I can handle bluegrass for about 10 or 15 minutes, and then I just start getting a little tense, right? It's like, so uh, uh, um, so yeah, I think that's at least one of the only. You know, I'm also really not into like death metal. I I understand what they're doing, and I do appreciate it, but I don't. I can't really get into that much. It's a little. Well, I can't say it's out there because what I do is probably more out there. But uh, um, all right, Ray. See you later. Thanks for coming in. Spread the word. I think you're subscribed. Make sure to hit the thumbs up if you desire, but spread the word because for the most part, we talk astronomy here, but music is definitely a thing that I'm interested in, and it does. Um, Music does actually tie into science, which ties into astronomy. So you know, all these things are sort of you know uh, uh, linked. Um, so yeah, but yeah, you know, at some point, let's get into this a little bit longer. I've already um, spent much more time um, than what I wanted to on that. But all right, cheers. Yeah, of course, prog rock. Yeah. So I wanted to expand a little bit on what I was talking about last night in terms of my photometry project. I think the real breakthrough that I had um, is or was one of those duh moments. Um, uh, so my system is old. It runs all of its data through a parallel port. So a full frame image takes about 15 seconds, 14 or 15 seconds to download from the camera to the computer so I can see an image. And that's very, very slow feedback, right? So what I realized, and this was sort of the duh moment, right, is that why don't I do what I'm doing when I'm doing my star alignment, and that is bin the image to make it actually smaller, right? So instead of taking a full frame image, right, what I can do is I can take 3x3 pixel sections and squeeze them into 1 pixel, right? And that can happen on the camera itself, right? Then I can actually decrease the size of the image by a factor of 9, right? It's 3 squared, right? 3x3. So instead of taking 15 seconds to download an image, it actually takes me about 3 seconds or so. Now, I'm not quite sure why it isn't exactly a factor of 9. There might be some overhead. There might be some processing, you know, that just has to happen, and that always takes the same amount of time. But anyway, with a feedback of about 3 seconds, right? So instead of getting a new image every 15 seconds, I'm getting a new image every 3 seconds. Well, that is better feedback, right? Better feedback. I'm going to turn this down a little tiny bit. It seems a little loud, and I don't want, although I like it, can't have it interfering too much. Larry, I should show you the camera that I am talking about. let me do that really, really quick. I don't think I've shown that off here anytime soon. I'll be right back in like 10 seconds. I just had to go and get it. So here it is. Here it is. And I'm gonna pull up my chat here so I can keep the conversation going. So there you can see if we can actually see the chip in there. I don't think that you can. Get it back here. No, do I have a light? Flashlight. Shine it in there. I don't know if you can see it or not. Probably not. No, there's too much reflection. Anyway, it's just a little CCD chip in there. I've got a, of course, there's a filter cap. I've got this thing here. This thing here is a filter wheel. So I've got I think there's 5 filter locations, and right now it has I think two open, no, one open slot, completely open, and then it has a clear. Is that right? Yeah, it's got a clear, whatever that means, and then it has an R and a G and a B. So, you know, the regular red, green, and blue thing. I'm not using any kind of filters with the work I'm doing. But anyway, this is let's see if the camera will focus. There we go. So it's an ST7ME, S big, monochrome, yes, yeah. This is old school. This is old school, but you can see a little bit of the electronics in there. There's the fan. This is thermoelectrically cooled. So I think, you know, TE cooled works pretty well down to about 30 degrees below ambient. So, you know, if it's 20 degrees C, it's pretty easy to get this down to -10 and not have it work too hard. But there we go. So there's the famous parallel port right there, and there's the power. This is a way to control the filter wheel if you don't have your normal means. I usually just do it through the parallel port. So yeah, so there's the camera. That goes, hopefully this will focus again. I'm gonna show you my ugly hand, and then we'll do that. There we go. So that just goes right onto the bottom right here, of course, the Cassegrain focus, like that, and then it just goes. So yeah, that is the camera I am talking about. Let's see. Oh, okay, this is just the filter wheel emblem on the front there. So yeah, that's just here we go. Cool. What does it say? All right. Yeah. So that's now. This is old school, right? I'm just a poor, penniless astronomer, right? So have to do things on the cheap. This is what I could sort of afford at the time, and you know, except for the slowness of the parallel port and the fact that it's a pretty small pretty small array, right? It's 765 by 510, right? So it's really, really, really small. So my field of view on this scope is 12 arc minutes, 12 arc minutes by 9 arc minutes. So 12 by 9. So yeah, small field of view, small array, pretty slow parallel port. So why do I have this? Well, like I said, I'm just a poor astronomer. I have wealth in many, 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 many ways, but those dollars, not very many of those. And that's okay with me because I don't want them. But the one saving grace of this camera is that the camera itself, the CCD itself, is a really good one. Really, really, really nice. It's low noise, pixel size. I think I said before that the pixel sizes were 13 microns. They're not. They're 9, which is sort of on the edge of being a little bit too small. Really, anything smaller than gets really. But this is a really nice low noise CCD chip, which makes for doing science really, really great. Really, really great. So, oh yeah, links to the here. I think I can grab that. I can grab that link, Tim, and project it up there anyway. I think I can do that. Copy link address and do that. Is that going to work? Okay, I don't know what this is going to do, so I'm just going to hit that. Oh, yeah, I don't know if I like that or not. Anyway, so yeah, definitely take a look if you're so inclined. The whole point here is that I realized, and this was sort of the duh moment, is that if I actually use the binned images, then my feedback is a lot faster, and I can actually find these targets infinitely faster, infinitely easier, super, super, super easy. If I can see that pattern, then I can zip right to it. So Andy, hey, nice to see you there. I could get an adapter, right? But it's not going to change the speed, right? It's not going to change anything. So I'm just going to go with what I've got, right? Because if I add an adapter, that's another piece of hardware that I have to worry about, and yeah, yeah, no big deal. And when I can upgrade, I most certainly will. But I am given a choice between having this and not having anything at all. This is awesome. This is absolutely fantastic. And as far as doing science, it's absolutely great. Absolutely incredible. Exactly, Larry. It works really, really well. It definitely isn't ideal, right? It definitely is not. But, when I get the opportunity, to make any kind of an upgrade, I definitely will. But I like this camera. I really, really like it. Now, I'm saying this with this camera right here listening to me, right? But I'm going to say it nevertheless, and that is there are better cameras, better, bigger, faster, less noise, blah, 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 right? But this works just fine for right now. So, you know, like I say, you know, you sort of have to deal with the cards that you're dealt. And yes, you can ask for a new hand, right? You can, you know, new game, whatever, right? But, you know, this is what I've got at the moment, and I'm pretty happy with it. In fact, I'm going to share my screen. This was sort of the next thing that I wanted to do. Anyway, really, really quick. I don't want to spend a lot of time here. Over on the Discord channel, I had posted this image a couple days ago. Now, this is this is one of those binned images. So this is a 3x3 binned image of a field of stars that I was looking at last night. So, you know, this is just raw data, right? So you're seeing all the artifacts, all these, you know, bad columns here and noisy pixels and everything, but there are definitely stars, right? Now, I sort of scaled this, so we're sort of looking way, way, way down into the muck, really, really low levels. And that's why the stars look like big, big blobs, right? This is typical. This is actually what these look like when you look way, way, way down into the muck, right? They just look like blobs, but these actually are focused. If you look at the fainter stars here, right, they're sitting on single pixels, right? So we're nice and focused. No problem at all. The reason why they're blobs is because of the optics. It just spreads that light out a little bit. In fact, it's called a point spread function. So yeah, here, let me, what I'm doing, of course, is I am taking a chart like this, where I have marked on here in red all of my targets that I want to get, right? And I mark 4 of them in purple because those are the 4 brightest ones, right? And if you see this rectangle here, this is the field of view of my scope. Now, let me back up a little bit. This is a 4-degree square field of view, right? So the moon, right, in this is about 1/2 a degree. So it's about this size, right? The moon is about this size or so, right? So as you can see, my field of view is much smaller than the size of the moon. So that sort of gives you a sense of scale here. So this is a 4 degrees in right ascension, 4 degrees in declination. And so this particular target that I was aiming for was actually this purple guy right there. So I'll sort of zoom in on that, and maybe I'll unmaximize that, bring them over here, and you can see, well, let's see, how can I do this? Let's just, how can I want to be able to show both of these on the same screen, kind of like that, right? So as you can see, this is this guy. This brightest one here is actually this guy, and then this dude down here is this one. And let's see, do I have that right? Do I? Or did I completely, do I have that totally wrong? Oh, I do. Yeah. I think, actually, yeah, I'm going to take a little bit of that back. I think, because I'm looking at the pattern here, I think, and maybe, wow, I might have this completely wrong now that I'm looking at it a little bit harder. I thought that that was the field, but maybe it isn't. So I'm thinking, I'm going to have to reevaluate that now. All right, well, put that on pause. I'll get back to you on that. It's sort of the astronomer's dilemma. All right, well, let's move on. This is sort of what I'm dealing with in terms of data, though. So it's nice. It's good data. No problem. But yeah, I'm gonna have to. I think I'm gonna have to reevaluate this because I don't think I'm looking at the same thing with the chart. So just like a typical scientist, you just can't decide anything. Yeah. Well, Larry, I take that as a compliment that it looks like a NASA image. I think that's a nice compliment. All right, well, cool. What I wanted to do was continue looking at the constellation of Corvus. So what I like to do here, we sort of call it the constellation of the day, but because usually these constellations contain a number of different objects, and I'd like to look at as many of these as we possibly can. And so one of the first things that I like to do is just sort of look at the boundaries of the constellation. So the International Astronomical Union has defined these boundaries for this particular constellation. So it's pretty small, right? It's only going from about 12 hours of right ascension to 13, and then from -10 declination down to what, about -25 or so. So it's almost a square, right? 1 hour of right ascension is actually 15 degrees. So yeah, this is pretty much 15 degrees east and west, 15 degrees north and south. We have pretty much a square here. They've just taken a little bit of a chunk out here. But as you can see, of course, it shows all the major stars of the constellation. Now, usually how the naming conventions go is that the brightest star is called alpha, right? And then the next brightest star is beta, next brightest star is gamma, et cetera, et cetera, et cetera. Well, here's another example. A lot of constellations don't follow this rule, and maybe someday I'm going to have to find out exactly why. But here's an example of that, right? Oh, let's get the music back playing here. There we go. So yeah, this is one of the constellations where Alpha is clearly not the brightest star in the constellation. Actually, Beta is. Now, the reason for that is probably historical, and we can probably look in here and see. But my guess is that the boundaries of the constellation probably changed, and so this star, maybe I'm just making sort of a wild guess, at one time maybe wasn't part of the constellation. And maybe this was Alpha, and because they moved the boundaries around, they had to rename them. That seems like a stretch. I'm not exactly sure why Alpha isn't the brightest here. Have absolutely no idea. We can try to find out, I guess. But here's all the other ones. Now these stars are pretty faint too. I think they were saying that Beta, which is the brightest. Let's see. Beta, where is Beta? Delta, Gamma, Epsilon, and Beta. Where is, here it is. Oh, nope, that's Gamma. Where is Beta? Don't we have a Beta here, or am I just not seeing it? Am I being completely blind? So I guess Gamma is the brightest star. So yeah, go figure, you know, Gamma is the brightest one. So why that isn't Alpha, I don't know. Like I said, you know, it's most likely a historical thing of some sort. So anyway, there's at least the boundaries of the constellation. These charts also show a few non-stellar objects, right? You've got a galaxy up here that's marked in red. It's like an oval in red outside of the constellation, but nearby looks like a globular cluster down here. It's a yellow circle with a sort of a plus sign or a crosshairs in the middle. So yeah, it doesn't look like much going on here to any extent, but like we saw in the last live stream, there are quite a few binary stars. There's at least a few variable stars. So I'd sort of like to dive into that. I'm going to take a look at the chat really quick. Okay, we're good there. Excellent. So let's see. Yeah, see, it's the 70th largest constellation, right? There are 88 constellations. So this is definitely one of the smaller ones. I guess they're saying that there are 3 stars that have planets. That's kind of cool. And let's see. I think that's about it there. So let's go down and see. We sort of covered all the info in Burnham's, and we actually looked at the antenna galaxies last time, which I'm pretty sure are these guys up here. It's sort of a cluster, right? We'll be looking at those a little bit more too. So so let's take a look. I don't think I'm going to dive into this too much. You know, these are all just sort of basic information about the stars, the distances, how bright they are, how they compare to our sun. In fact, what Gamma, right? Gamma, they're saying is 4.2 times the mass of our sun. And 355 times as luminous, as bright. So it's 355 times brighter than our sun. That's mainly because it's a B star. B stars are pretty massive and therefore very hot. And when they're hot, they burn really bright. So yeah, you know, the fact that it's 4 times the mass of our sun, I'm not surprised that it's 400 times the brightness of our sun. But wow, pretty young, right? 160 million years. That's not very old at all. I mean, our sun, at least, you know, as the story goes at the moment, right? Our sun is about 5 billion years old. So, you know, this is like just a baby compared to our sun, right? It's 160 divided by 5,000. So that's 3.2% of the age of our sun. So, yeah, what? If somebody lives 100 years, that's like a 3-year-old, right? So, so yeah, this is just a little one at the moment in terms of youth. In terms of size, right? It's like a big baby. Yeah. Let's see. So it sort of looks like too that Gamma is a binary star. That's kind of cool. And so this B star has a red dwarf star companion, right? Spectral type K or maybe M, right? So that's low mass, low temperature, and therefore, you know, not very bright. But look, it's almost actually the same size as our sun in terms of mass. Does it say anything about luminosity? No, I don't really see anything there. And actually pretty close too, right? So the companion star to Gamma is about 50 astronomical units away. Pluto is about 30 astronomical units away from the sun. Ultima Thule, the asteroid that the New Horizons spacecraft is going to pass by in a couple weeks, I think it's about 40 astronomical units away. So this companion star to Gamma is about 50 astronomical units away. And of course, an astronomical unit is the distance between the Earth and the sun. Completes its orbit in about 158 years. Okay, cool. So Delta Core is a visible binary star. So that's Delta here. Let's why don't we take a look at Delta Core with and that's this guy up here. Why don't we go over to Simbad really quick and take a look at Delta Corvus. Let's see, I'll just tromp on Nightbot here, pull up Simbad. Simbad is absolutely fantastic for this kind of stuff. So let's just do Delta, I think it's Corvi. Find out. Yeah. Yeah, I think we can actually tell that there are 2 stars in there. What is there a Sloan digital sky survey of this image or of this star? Oh, it doesn't look like it. Doesn't look like it. It's sort of, you can almost tell that it's a binary though. Let's see. This is going to look really weird for a second. It's going to be all blown up. We'll back it out a little bit. Weird optics here, lots of reflections and lots of weird stuff going on. But yeah, so apparently this is a visible binary star. I'm not really seeing anything because, you know, I mean, it's so overexposed, right? So yeah, kind of hard to tell. So let's go back and see. So I guess this is what's called a high proper motion star, which means that it seems to be moving really, really fast in the sky, relatively speaking, right? This is milli-arc seconds per year, right? So an arc second is 1/60th of an arc minute, and one arc minute is 1/60th of a degree. So one arc second is 1/3600th of a degree, and this is milli-arc seconds, so it's 1,000th of an arc second. So, when we're talking about large motions, you have to kind of hold that in perspective, right? So over the course of 1 year, right, and I'm going to pull out my calculator again, because what we're going to do is we're going to add these two numbers up in what's called quadrature. So I'm going to take the first one, 210.49, and I'm going to square it, squared. And then I'm going to add that to the square of the second one, 138.74 squared. And then when I add it, I'm going to take the square root of that sum. And that's going to give us 252 milli-arc seconds per year. So about 1/4 of an arc second every single year, right? So in order for me to see any motion at all on this star, I would have to wait about 4 or 5 years, because the resolution I've got on this this scope with this camera is about 1 pixel, maybe a little bit less, and each pixel on my camera is almost an arc second. So yeah, for me to detect any kind of motion of this star at all, I would have to wait 4 or 5 years, which is actually a pretty short amount of time. These numbers are usually much smaller, much smaller. And it's just because of the distances, right? And also the relative velocities. So let's see, it looks like it is moving away from us at 13.9 kilometers per second. And here they're calling it an A0 star, an A0, which is also, pretty blue. What does we're looking at delta. What else does Wikipedia say about delta? Yeah, okay, blue-white star, magnitude 2.9, surface temperature of 10.4 thousand K. Our sun, I believe, is about 5,000 or 6,000 K, so this is about twice as hot. And again, very, very young, very, very young, 3.2 million years. That's like nothing, right? But I guess they're not quite sure if it's either sort of a young star, that hasn't settled down, or is an older star that is sort of also settled down, but past this weird stage. Yeah, so A0, cool. Okay, so I guess, yeah, it does have a companion, an orange dwarf star, 650 AU. Okay, so 5.4 arc seconds. So, yeah, that is going to be buried inside of that muck for sure. Yeah. So there actually is another star in there, much fainter, and not visible there. We could probably go over to Gaia and get it that way. But then I'd have to make a chart, and yeah, that's too much work for right now. So, well, cool. Let's sort of see what else Delta Core has here. There, let's see, lots of references, lots of different names, right? Lots of different names. Let's see, does any stand out? Not really. You know, Gaia Data Release 2, of course, is in there. Here's its common name, Algorab. Pretty cool. You can impress your friends by saying, see that star? The upper, what is that? The upper left star of Corvus. You can tell all your friends that its name is Algorab, and they'll be extremely impressed with that. Lots of references. Good. Let's look at the distance and velocity measurements here. I always like to see how consistent all these are. It looks like there's only one distance measurement here, almost 26 parsecs away. So a parsec is 3.26 light years. So 25.9839 times 3.26 is 84.7 light years away. So actually pretty darn close. And that explains its high proper motion, right? Because it's pretty close. You know, just like Comet 46P right now, right? It's as close to the Earth as it's going to get, by the way. Happy perigee for that comet. And because it's so close, it's really appearing to be moving really fast, really fast. And that's just because it's so close. And the relative motions between the Earth, us, and it are different. And so we're going to see these things moving quite a bit. So, you know, the fact that it is pretty close does explain why it seems to be moving so fast across the sky. So kind of inconsistent measurements here, but some of these go way back, right? 1929, 1937. So, you know, with improved technology, we can make our measurements and probably be more accurate. So I would trust these you know, newer measurements here. It sort of depends on the technique and everything, but yeah. So here's some measurements of the proper motion. So pretty consistent there. Pretty consistent in terms of temperature. Pretty consistent in terms of parallax, which is sort of a that's an indication of distance. So yeah, sort of consistent here. Here's a 22.3, which seems a little low. So let's see. There are a bunch of references, 177 of them. Wow. We're definitely not going to be able to go through all those, but we can look at a few of the most recent ones. Yeah, so I guess this has some kind of a debris disk. Wikipedia said something about that too. Let's see. Amateur telescopes. 2.7 times the mass of the sun. 65 to 70 times as bright. Yeah, so I guess they detected a circumstellar disk, right? So this is, at least as the story goes, this is some kind of disk of maybe it isn't a disk. I guess they're saying dust. Just a bunch of dust around this this guy, and that kind of helps us confirm our ideas about how solar systems are formed. You know, the story goes that you know, suns form in these clouds of gas and dust, but there's a lot of residual left over, which goes into the forming of planets and moons and asteroids and comets or anything. It's a good story. I don't know if that's how it actually is or not, but our observations, you know, fit those models pretty well. So, you know, our confidence is high. So yeah, I guess they have found a similar kind of a circumstance here with Delta Core, and so that's kind of cool. Okay, so here's another binary star, pretty close to one another. That's kind of hard to see with an amateur scope, but you might be able to do that. We could actually look for Struve 16692 at some point. Like I say, you know, even these small constellations, right, are filled with just absolutely amazing, unique things, and always something new to learn here. So, but hey, you know what? I am looking at the time, and I'm noticing that it is 3:12 UTC, and I try to keep these live streams to a little over an hour. I don't like to go too far because I do respect everybody's time, and I greatly appreciate everybody who comes in here. But I think for now, I'm going to let you go. I'm going to stop sharing, get back on there. I'm going to check the chat really quick. Yes, the Electron rocket is launching. I think it's Tom. I heard a launch time of somewhere around 6 hours UTC, so that's coming up in a few hours. And yeah, that's a nice big launch window there. So yeah, you know, those folks are doing some great, awesome work, and we need more of those. I'm really looking forward to Blue Origin doing their thing. Virgin Galactic this past week got their rocket up and had a successful flight. You know, they opened the door to all the controversy in terms of, you know, did they actually get to space or not? And you know, that's, I don't know. I think people spend a lot of time wasting a lot of effort on those kinds of arguments. You know, my attitude is that everything seemed to work. They did what they wanted to do, and you know, on to the next thing, right? It's like they did it, right? So, you know, whether they got into space or not, I don't really care. But Virgin Galactic is definitely going for the space tourism thing, for absolute sure, right? They want to give people that ride, and I think that's great. Yeah, that is definitely not anything that I'm interested in at all. Not really. You know, given the opportunity, I probably would, but I'm not going to, you know, pony up the bucks and do it because I want to. Being asked, oh yeah, I probably would. But my thing is a 7-day cruise to the moon and back, right? You launch, you spend a day or so going around the Earth, and then shoot to the moon. Takes a couple days to get there. You zip around it, right? That just takes a few hours. And then you come back. That takes a couple days. Go around the Earth a couple more times, and then land. That's what I want to do. So hopefully, you know, if the costs keep coming down, Elon Musk, right? Elon Musk is saying $100 a pound. $100 a pound. So you know, think about your weight and multiply that by 100, and then put a dollar sign at the beginning, and that's how much it would cost, right? If you want to bring some luggage along, you know, there might be extra expenses too, but you know, $100 a pound, that is affordable, right? That's almost affordable. It's at least a thing where, you know, if you wanted to, you know, like open a credit line and, you know, or get a loan or something, you know, for $10,000 or $20,000, I'd go to the moon for sure, for sure. Yeah, easy. You know, I've actually started saving my dimes. So yeah, I think you know, if things go the way that they're going, I definitely see that in the next, you know, 20 to 30 years. Definitely. All right, you guys, I'm going to get out of here for now. Hopefully the Electron rocket will launch. I think they do have a payload, or payloads. I'm sure they do. So I hope that that's a success. It's extremely exciting. You know, I haven't heard anything about the Chinese landing on the far side of the moon. Haven't heard anything about that. Haven't really been looking. But you know, I try to stay at least aware. So you know, if I'm not actively looking, I am usually actively listening. But haven't heard anything yet. I think I posted over on the Discord that maybe a radio signal was heard, but yeah, I don't know if that's confirmed or not. So I mean, they would have gotten there by now, I would think. So yeah, I don't know how any of that is going, and it's frustrating, right? Because I would love for all of us to be going on that, right? Not just, you know, one group, right? I mean, we're all one planet. Let's go together, right? But we're not there yet. Hopefully, also in 20 to 30 years, I'm hoping that we're going to get there, where it's like, you know, it's absolutely ridiculous to, you know, compete like this and have secrets and you know, because I mean, it's basically the same thing, right? I mean, if you want to go to the moon, you've got to do A, B, C, D, and E, and so you know, why should it be that, you know, group number one does A, B, C, D, and E and gets to the moon, and group two does A, B, C, D, and E and goes to the moon, and group three goes, you know, it's like, let's all do it together. Buckminster Fuller, right? He had this idea of synergy, right? And there is synergy when we combine our efforts. You know, I mean, if we went to the moon as one planet, oh, that would be absolutely amazing. You know, the kinds of stuff, you know, that we could do. It'd be so much easier. It'd be cheaper for, you know, each contributor. it'd be great, right? So let's do that. Let's at least move in that kind of a direction. But in the meantime, we can root for the Chinese at sort of a distance. They're not going to let a lot of information out because they're as paranoid as we are. So hopefully that'll change. I really hope it does. The only thing that we can do, to quote another great mind, Gandhi, right, is to be that change, right? I mean, we can do it. I mean, we can be that change. If we change ourselves, we change everything. So let's do it. Let's get to the moon. Let's do all those great things that we want to do. Our ability is limitless, right? We can literally do anything we want. We just have to decide to do it. So let's do it. Let's go. Let's go. So, all right. Well, with that, I'm going to get off the soapbox and I'm going to get out of here. A reminder or a piece of info. This is Solstice week, and it turns out that I've been invited to a solstice celebration. So there will be no live stream for the 22nd of December. No live stream that day, because for me it'll actually be the evening before, right? The evening of the 21st, and I'm just not going to be here. So I'm going to be out looking at the sun and celebrating the end of the darkness and the beginning of the light. So that should be fun. I will definitely remind you all this coming week that there is not going to be any live stream on the 22nd. So, all right. Well, for now, I'm going to get out of here. So peace, cheers, and all of that. Have a great evening, a great day. Make sure to subscribe if you haven't. Hit the thumbs up, thumbs down. Make some comments. Spread the word. Spread the word. I'd like to get a nice, sizable crowd in here. Now, I'm not aiming for thousands and thousands and thousands, but I think having a nice panel down here, having a discussion, and having a sizable group in the chat, keep that going and active. I think that'd be absolutely awesome. So definitely spread the word. I know that this time isn't great for everyone, but we've got some crazy people in this world who like to be up at 2 or 3 or 4 in the morning. I won't name any names, but they can appear here from time to time, and I think that's awesome too. That's really, really, really great. Greatly appreciate everyone who comes in, because I'm just here. I'm sharing a passion. I'm not trying to teach anything. I'm not really trying to communicate anything. I'm just sort of thinking out loud and doing what I've done for years and years and years, and that is sit back, relax, think about astronomy, think about space and science and music, and share that passion with all of you. So this is great fun. I've actually been doing this now for 11 months. So okay, that's okay with me. It doesn't seem like it's been that long, but that's great. That means that I must be having a lot of fun. So, all right. Well, speaking of fun, I'm going to get out of here for now. So take care, everybody, and I will see you in a little less than 1 Earth's rotation. So take care. Peace, cheers, and all that. See you later. Bye.